Now we will talk about synthesis of alcohols. A lot of it you've done before, and there are some new synthesis in here. So here is a little bit of a summary of synthesis of alcohols, and you will recognize a lot of these reactions. Most of them are coming from alkenes actually, okay? And but the thing is that alcohols can be synthesized from a variety of functional groups, and we will cover almost all of them over here. We've done the nucleophilic substitution, okay? So that is one of them. And then we did a whole bunch of reactions in alkenes where we had the hydration using acid solution, oxymercuration, hydroboration, and then we had the diol synthesis with osmium tetroxide and potassium permanganate. And then we can also make diols from epoxide. So it's not a direct synthesis, but you take an alkene, convert it to an epoxide, and then make a diol from there. So here we have a whole bunch of synthesis given of alcohols. The interesting thing about alcohols in this little chart here, okay, is that this little arrow, okay, that you see in all of these. And what this means is that you can convert any of these functional groups to alcohol, and you can convert alcohol to any of these functional groups. So it tells you really that alcohols are extremely versatile, okay, which also means that you have to be careful if you have an alcohol as a functional group because it can undergo so many reactions. However, it is kind of nice because now you have a variety of ways that you can actually make alcohols and a variety of things that you can make from alcohols. So it's kind of all very interesting. So we'll start with the synthesis first using alkenes. Okay, and in case of alkenes, this is kind of a quick review because you've done this before, and if you've forgotten anything, then please go back to the alkene chapter and review all of these things. Although a brief summary is given over here, but still there are some mechanism points that you might need. So please go back and review all of those. So the first one here is acid catalyzed hydration of alkenes, where you take an alkene, treat it with an acid, and of course with the acid you also have water, and that's the hydration part that's going on. And so then you have the water attaching to the double bond, giving you an alcohol. The interesting thing about this one, or the key thing about this one, is that this is a Markovnikov addition. And the problem with this kind of a reaction was, if you remember, is that because this goes through a carbocation mechanism, that rearrangement is possible, okay? And which is why sometimes you're not able to do this according to what you need. And for that, we have oxymercuration and demercuration. And in this case, this is still a Markovnikov addition, but there's no rearrangement because the mechanism does not involve formation of carbocation. However, you still have a Markovnikov addition, which still leads you to something that you would have made before. So in any case where you have an alkene and then you treat it with mercury acetate and then work up with sodium borohydride in an alkaline solution, and you end up getting an alcohol. Then we have hydroboration, and hydroboration is of course the anti-Markovnikov addition, where you take an alkene, treat that with borane in presence of hydrogen peroxide and a base, and you end up getting anti-Markovnikov. And again, if you need to look at the mechanism, go back to the alkene chapter and review the mechanism, okay, for borane. And then there is halohydrin formation. In halohydrin formation, you're not only getting an alcohol, but you're also getting a halide on the alkene. So it's an addition reaction. It's not exactly a synthesis of alcohol. However, you can get an alcohol, but you also get a halide over here. So depending on what you're trying to make, you can use the synthesis. So here's an alkene. The first thing you do is treat it with bromine, and bromine forms this bromonium ion, and the alcohol, then the water, will then attack the carbon that is more substituted. Remember that, okay? Because this is the one that is stabilized. So in a way, this is still a Markovnikov type of an addition, okay? And so then this opens up. And the important thing about the halohydrin formation is that this is an anti-addition, okay? Because the alcohol and the bromine, they will attach on opposite sides. So this is an anti-addition reaction. Then for the diol synthesis, we're still in alcohol synthesis, and now we're not getting just one alcohol group, we are now getting two alcohol groups. So here we take an alkene, treat that with osmium tetroxide, and then work it up using sodium sulfite, and you end up getting a diol. Now in this case, the alcohols are going to be what we call syn addition, SYN, and it's a syn addition due to the mechanism of the reaction where osmium tetroxide comes from one side of the alkene, okay, and then you get the two alcohols. You can do the same reaction with KMnO4 provided it's cold. Okay, you can't do it with hot because that would cause cleavage of the alkene. So use KMnO4 cold in presence of basic solution, and then you also still get the diol. And again, this is a syn addition. The problem with osmium tetroxide is that it's very toxic, and the problem with KMnO4 is that it's very messy because it's a very powerful oxidizing agent. You have to be very careful that you don't have any other groups, okay, on there. So anyhow, this is how you form diols, and this is a syn-diol synthesis, okay, which means alcohols on the same side. And here we have the diol synthesis using epoxides. And again, we will talk about this one using ethers also when we get to the ethers chapter. But this is just an introduction so that you know how to make different kinds of diols. So here we have an alkene, and you treat that with a per acid, and you get an epoxide. Once you have an epoxide, then you can open up the epoxide ring using acid or base hydrolysis. So this mechanism that's given over here is acidic hydrolysis. You can look at the mechanism, it's pretty straightforward, but we will do this in great detail when we get to the epoxide chapter. Okay, however, it's very straightforward. Okay, here is your acid, and here is the base. The base picks up the proton, it becomes protonated. So here's the oxonium ion. Once you have an oxonium ion, it has to get relieved, and therefore a water comes in and attacks from behind over here. And then once it attacks this carbon from behind, this bond opens up, and then here is the oxonium ion, the new oxonium ion now, and that gets deprotonated from another water molecule. And here is that alcohols. And now you can see that this alcohol group, which was coming from behind, therefore these two are now going to be anti. Okay, so the previous two syntheses that we did with osmium tetroxide and KMnO4, that was a syn addition, and this is an anti addition. Now remember, in all these three reactions, you're also going to get an enantiomer. We're just not writing it, but you will get the enantiomer. This is still a continuation of epoxide ring opening, and in this case we're going to talk about the base catalyzed reaction. In the previous one we were talking about acid catalyzed. In the acid catalyzed, the epoxide ring started the reaction, but in a base catalyzed reaction, the base is going to be the nucleophile. So this will be like a typical SN2 kind of a mechanism where you have as we say, a backside attack. All right, and so pretend that this R group is a H, okay, which means that this is a hydroxide. So if this hydroxide comes in and attacks this carbon, which is the electrophile because of the polarity with oxygen, okay, of the carbon-oxygen bond here. And so when this hydroxide attacks this carbon, this bond opens up over here, gives an oxide ion, and that oxide ion will then pick up a proton from water. Okay, and so then it will become hydroxide over here, which is an alcohol group, and here also you have an alcohol group. Now, since this was in backside attack over here and the epoxide ring is opening up from the front side, then this will still give you an anti-addition. Okay, so both acid and base catalyzed both give an anti-addition of alcohol. So depending on what kind of other functional groups you have, you can choose either of these hydrolysis. So another common way of making alcohols is by reducing carbonyls. Carbonyl compounds are anything that has C double bond O. So for example, aldehydes, ketones, carboxylic acids, and esters. First, I want to just go over a little bit about oxidation reduction in organic chemistry. And the first part here you have done before, which is hydrocarbons. In hydrocarbons, there are three classes that we generally talk about: alkanes, alkenes, and alkynes. And alkanes are the one with the maximum hydrogen. With alkenes, you lose 2, and then alkynes, you lose 2 more from an alkene. So when you go from an alkane to an alkene by losing 2 hydrogens, that process is oxidation because that is loss of hydrogen. Going from an alkene to an alkyne is also loss of 2 hydrogens, which is also oxidation. This is represented right here by these oxygens. Now these oxygens in square brackets, that means there's active oxidation going on, but it doesn't necessarily mean that you're adding oxygen. Okay, it just means this is an oxidation step. The reverse of this is going to be then reduction, because if the forward process is oxidation, the reverse has to be reduction. And so with case of alkyne to an alkene, you're adding 2 hydrogens, which is very traditional reduction. And then going from an alkene to an alkane, you also add 2 hydrogens, which again is reduction. So this is oxidation reduction going on in hydrocarbons. When we get to oxygen containing compounds, we have alcohols, carbonyls, and then even more carbonyls as in the acids. Okay, and so what does this mean, like as in more carbonyls? It just means that you have more oxygen in the acids over here. So going from an alcohol to a carbonyl compound, you lose 2 hydrogens because you have one double bond now. So you lose 2 hydrogens. Once you lose 2 hydrogens, that is again oxidation step. Going from a carbonyl as in an aldehyde or a ketone to an acid, you actually add oxygen, and that is your very traditional oxidation. Okay, where you're going to be adding a reagent that actually has oxygen, unlike the first one. Again, the reverse of all of this is reduction. So going from an acid to a carbonyl, you remove an oxygen, so that is reduction. And then going from a carbonyl here, aldehyde or ketone, to an alcohol, you actually add hydrogens, and that is also reduction. In this case, with alcohols chapter, we'll be talking more about the reverse step, which is reduction of the carbonyls, whether it is aldehydes or ketones or acids and esters. Okay. Now, regarding the aldehydes and ketones, remember this example right here is actually for an aldehyde, but you can very well have a ketone here. Similarly here, this is an acid, but you can also very well have an ester here by replacing this hydrogen with a carbon. Okay, and so all of those can be reduced to form alcohols. So reduction of carbonyls. Here is an example of what's going on here. All right, again, so this is the carbonyl. This is the active hydrogen, as we call it. The hydride or the active hydrogen can come from anywhere. Okay, so it's just a reducing agent. It's just a reducing step. What reagent you actually use is something that, depends on what kind of reaction you're doing. And then of course you get an alcohol over here. So here are 2 examples, one using an aldehyde and one using a ketone. And if you use an aldehyde, and aldehydes are considered to be terminal groups, and terminal because they are found at the end of the chain or in a ring, outside a ring. So when you reduce aldehydes, you will end up getting primary alcohols. When you reduce a ketone, which is an internal group which is surrounded by 2 carbons, if you reduce those, you will get a secondary alcohol. There is no doubts about this. There's hardly any discussion about this. Okay, so this is a given. Aldehydes will give primary alcohols and ketones will give secondary alcohols. Now, what is this active hydrogen? Those are, of course, the reagents that we talk about. So the reducing agents here are going to be sodium borohydride, NaBH4. The H4 here are the hydrides. These are the active hydrogens that are actually causing the reduction. And then lithium aluminum hydride is also a good reducing agent. However, it's very strong and it's a little bit hard to work with. Okay, and so if you're going from an aldehyde and a ketone to an alcohol, then sodium borohydride is the reagent of choice. So here is an example, okay, of an aldehyde reduced with sodium borohydride to give an alcohol. And again, because this is an aldehyde, you end up getting a primary alcohol. Here we have a ketone, and if you have a ketone, you will end up getting a secondary alcohol. All right, so that's a very simple kind of reduction going on here. In your textbooks, you also may have hydrogen, H2, which is hydrogenation going on. The problem with hydrogenation is that if you have any other group in there, for example, something like a nitro group or an alkene group, then you also tend to reduce those. So you have to be very selective in what kind of reagents you choose and what other functional groups you have in there. A little bit about the mechanism of this reaction. Here is your carbonyl. Here is the active hydride. Now remember, this is a hydride, not an H plus, but H minus. Okay, because H minus, this is bonded to sodium. So if sodium is positive, hydrogen has to be negative. And so this is the hydride. And if this is the hydride, this is what we call the nucleophile. The nucleophile will attack the electrophile, which is the carbon over here. Again, the carbon is always going to be the electropositive center. So the hydride attacks the carbon, these electrons move to oxygen, so you end up getting this intermediate, which then in treatment with acidic water, you end up getting an alcohol. Very simple step to do, very easy reaction, and usually ends up giving good yields also. Very straightforward, unless of course you're using lithium aluminum hydride. Reduction of acids and esters. Now, acids and esters are slightly different from aldehydes and ketones because acids and esters are more oxidized, which means that they have one more oxygen in them than aldehydes and ketones. The other thing about carboxylic esters and acids are that these are terminal groups, both of these. Okay, now esters are not really terminal, they're internal, but for the purpose of reduction, they're considered to be terminal groups. And because they're terminal groups, they will only give primary alcohols. You cannot make secondary alcohols using acids and esters. Also, the other part, because they have two oxygens in them, you need a stronger reducing agent. So sodium borohydride is not going to be very effective, and you need to use something stronger. So lithium aluminum hydride is now used for carboxylic acid and ester reduction. It is still better to use esters for reducing rather than using acids. Okay, the yields are okay, but the yields are much better for esters. There's also the fact that you have carboxylic acid, which has an acidic proton. So if you have an acidic proton and you have an active hydride, the hydride may tend to react with the acidic proton over here, okay, to produce hydrogen. So, to eliminate the possibility of that side reaction, it is much better to start with an ester and then reduce that using lithium aluminum hydride, and you end up getting alcohol. Again, remember, you will get only primary alcohol using these reducing agents or using, esters and acids. Now, alcohols from Grignard reagent. This is really a big topic because now we get introduced to something which is called organometallic reagents. And there are three kinds of organometallic reagents that you will encounter. The first one are lithium reagents, then there are magnesium reagents, and then copper lithium reagents. Okay. In all of these cases, you can see that there is a metal involved. And if there is a metal, the metal has to be positive, which means that if the metal is positive, then the R group or the carbon that is attached has to be negative. So this is your first introduction to carbon anion. You had a little bit introduction before with alkynes also, but this is true organometallic chemistry using alkanes. So the R group here is going to be the carbon anion because it is bonded to a metal, and metals can never be negative. Okay, they're always going to be positive, and therefore the R group is going to be negative. So what's the difference between lithium reagents and magnesium reagents and the copper reagents? Well, lithium is in group 1, alkali metal. Okay, alkali metals are one of the most electropositive elements on the periodic table. And then magnesium comes in, which is alkaline earth, which is a little bit less electropositive. And then copper is a transition metal. Okay, so there is a varying degree of electropositivity. So as you go from lithium to magnesium to copper, the metallic property of these elements is changing slightly. So the lithium reagents are highly metallic, okay, which means that lithium is the most electropositive metal, which means that the R group here is extremely negative, okay, whereas the R group here with the magnesium, a little bit less negative, and the R group here with the copper is also negative, but not as negative as it would be with magnesium or lithium. What does that mean that if something is a little less negative? What that means is that the anion is way stronger with the lithium reagent than the anion with the copper reagent. And what that gives you as an advantage is that the copper lithium reagents, for example, will be a lot more controllable. Okay, because the anion is not very reactive. Okay, and so sometimes you can get really unusual reactions also with the copper lithium reactions with the reagents because the anion here is not very reactive. Okay, so first of all, you have a lot of control, and the second thing is that you can create something completely different and unpredictable. Okay, I mean, you can predict it, but the thing is that you will not get the same products that you would for lithium and magnesium reagents. The magnesium reagents were actually the first one to be synthesized, and they were synthesized by Victor Grignard. Okay, he was the chemist who first made them, and hence these are known as Grignard reagents. The lithium reagents are very powerful, very, very strong. So if you know what you're doing, you want to do it fast, and you know that you will not have any side products, then you use lithium reagents. Otherwise, magnesium reagents, the Grignard reagents, are very manageable and easy to work with, not that hard so long you control some of the environment. You're pretty much okay. So that's the difference between these three different organometallic reagents. We will deal with these two as if they kind of work the same way, although we know that the lithium reagents are a little bit more reactive than magnesium, but they kind of behave the same way. The copper lithium reagents we will not talk about over here because they're a little bit different. Okay, one of the key things about working with organometallic reagents is that you have to work with them in a completely moisture-free environment, which means that there should be no water present, okay, at all, because the carbon anion here that we have is a very strong base. Now remember, the carbon anion is coming from an alkane, which is not a very good acid. So which means if it's not a good acid, it's giving a very strong conjugate base. So if it's giving a very strong conjugate base, it will react with everything and anything that is even slightly an acid, which water is, okay? And so therefore you cannot afford to have any water or alcohol, okay, in the environment. So water, alcohol is out as a solvent and water is out, which means that you can't even have your reaction going on in an open atmosphere. You have to kind of keep it closed. So that's an important part, okay, for working with Grignard reagents. Regarding how to make the Grignard reagents, it's really very quite simple. You take an alkyl halide, treat that with magnesium, and magnesium comes in different ways. You can get powdered turnings. Turning is like small pieces, and then treat them together. If you kind of stir them together, then you end up getting the magnesium reagent. Once you have the Grignard reagent, then you can go ahead and add the other component of it in order to make the alcohol, which we will get to now. Okay, but that's how you make Grignard reagents. So the general reaction is that you take a Grignard reagent, treat that with an aldehyde or a ketone, and that will give you an alcohol. Okay, and we will talk about what kind of an aldehyde you use, or whether to use an aldehyde or a ketone, which one. But however, the thing is that you need a carbonyl compound in order to get an alcohol with the Grignard reagent. Okay, so this is the general reaction. Here is your carbonyl, which could be an aldehyde or a ketone, depending on what the substituents are. And then here's your Grignard reagent. You have to use ether as a solvent because, as I just said, you can't use any alcohol. Okay, and this is written as step number 1, and this is step number 2. You cannot use water, okay, in this reaction, so which is why this is the second step, and we will see in the mechanism how this works, okay? But anyhow, this is how you get the alcohol then, and then you have all of these other inorganic products that are formed, which are then removed when you work up the reaction. Here is an example of what happens to your Grignard reagent if there is any water or alcohol present. Okay, so the H here can be R also, which means CH3OH or an ethyl alcohol. So in any case, if you have an OH present, if you have an acidic proton present in there, then the Grignard reagent, this negative carbon over here, okay, will pick up the proton, okay, from this acid, and it will end up giving an alkane, okay, because it's a strong, strong base. It will pick any kind of a proton, okay, even the weakest proton possible. And so you end up getting an alkane, okay? When you get an alkane, literally what you've done is destroyed your reagent. So unless you want to destroy your reagent, you don't want to have any alcohol in there, okay, or water in there. So that is why in the second step here, during the workup, you can use water, because then you can also get rid of any of the extra reagent that you have. Here is the mechanism at the bottom, and the mechanism is very straightforward. Only two-step mechanism for this reaction, where you start with the carbonyl. Now remember again that the carbon here is the electropositive and oxygen is the electronegative part. So here comes the carbon anion. The magnesium is still there, okay? We're just not writing it out here, but it is here. That carbon anion will attack this carbon, the carbon of the carbonyl. Electrons move here, and then here you have the oxide. Then you treat it with the acidic water, and that protonates your oxide. If you remember, we just did the same mechanism with the hydride also. In case of hydride, you had H minus. In case of Grignard, you have an alkyl group. Okay, so now the alkyl group will attach over here. Okay, whereas in case of hydride, it was hydrogen that was attacking over here. If you don't remember what I'm talking about, just go back to slides, okay, and you will find it. So in any case, this is how you would make the alcohol, and this is the mechanism of it. You have to please make sure that you write this in step number 1 and step number 2. Don't write water along with the Grignard reagent because that is completely wrong. So step number 1 is Grignard reagent. Step number 2 is acidic hydrolysis, okay, to give the alcohol. Now let's talk about exactly what kind of carbonyls we can use to make the alcohol. So here are 3 reactions we'll talk about. Reaction with formaldehyde, reaction with any other kind of aldehyde, and then reaction with ketone. The first reaction here with formaldehyde. This is the structure for formaldehyde, HCHO. And this is the first aldehyde possible in case of the aldehyde family. And here's the Grignard reagent, all right? So you're getting the alkyl group from here. And when you react the Grignard reagent with formaldehyde, here's the intermediate. The final product that you end up getting is actually a primary alcohol. All right, so here is how the mechanism works, which means one R group is going to be attacking the carbonyl, and here is the R group now that is attached here. Okay, and the 2 hydrogens were already there to begin with in the formaldehyde. So you end up getting a primary alcohol. Now look at the difference when we do for the aldehyde reaction. In the aldehyde reaction, you still have the Grignard reagent, the R group, which could be any alkyl. And here is now, instead of hydrogen, you have an alkyl group here for the aldehyde. So which means that this could be CH3, C2H5, or any other bigger aldehyde. Doesn't matter, not formaldehyde. That's the main thing. So which means you already have an R group there. Another R group comes from the Grignard reagent. And when you finally work this reaction up, now you have 2 R groups. So which means you've ended up synthesizing a secondary alcohol. So which means that formaldehyde will always give you a primary alcohol, and the other aldehyde will give you a secondary alcohol. And then the last reaction over here is with ketones, and in ketones, both of the H's, okay, that you saw in formaldehyde are now R groups, which means that the final product that you end up getting is 3 R groups over here, and then you have a tertiary alcohol, okay, because 2 R groups were already present. 1 came from the Grignard reagent. So this is a nice little colored scheme to show you where the R group is coming from and what R groups you already had. The nice thing about Grignard reagents and treating them with aldehydes and ketones is that you have a way of making primary, secondary, and tertiary alcohols. We didn't have that choice when we were treating carbonyls with hydride, which is the reduction. In the reduction, we had the choice only for primary and secondary alcohol. We could not make tertiary alcohols, but now we can, okay, using ketones. So this is really a nice, versatile way of making alcohols. Here are some specific examples now, okay, because in the previous slide, I had just given R groups, and now here are some specific examples. So for formaldehyde, if this is your Grignard reagent, then this is the R group that you're adding on, and here is the R group that you added on to formaldehyde. So the 2 hydrogens for formaldehyde are right here, and then of course the alcohol group comes from the carbonyl oxygen. Then here is a secondary alcohol synthesis using another aldehyde. So here is an aldehyde. Any aldehyde, okay, it doesn't really matter, but in this aldehyde now you have a longer chain over here of carbons instead of the 2 hydrogens. So on one side you have to have the hydrogen because it's an aldehyde group. On the other side you have an alkyl group. So now when the Grignard reagent reacts with this, you end up getting all of this which was with the aldehyde, and here is the R group that you got from the Grignard reagent, and of course here's the alcohol, secondary alcohol. And then here is the tertiary alcohol now with a ketone. Okay, and ketones are internal groups as we talked about, and therefore you can actually have cyclic compounds. So this is a cyclic ketone. Here is the Grignard reagent. This is the R group. The R group will attach right here. So you end up getting a tertiary alcohol in this case. In all of these cases, you will see that the yield is pretty okay, which means this is a nice synthesis to work on in case you want any kind of an alcohol, which is why Grignard reagents are very popular. The only thing you have to be cautious of course, is the water in the system, which means that you should not have any any water, okay, or alcohol for that matter. All right, so all the solvent over here is ether, and then you work up with the acid water in order to protonate the alcohol, but otherwise no water or alcohol in the system unless you're working up. Now let's look at this reaction with esters also. We did the similar kind of reaction with esters and reduction, if you remember. It's the same kind of thing because there the nucleophile was the hydride. Here again the nucleophile is an alkyl group. So essentially you're getting the same kind of thing, all right? However, the reaction is slightly different with esters. If you remember previously with esters, the reduction gave you a primary alcohol, all right? And here it's actually going to be a tertiary alcohol. So let's see how this works. You can take any ester, all right, and an ester group is an internal group, so which means that you have something on the left side of the carbonyl, and of course with the oxygen here, you also have an alkyl group. So this is an ester, and now in this case, you will actually need 2 moles of the Grignard reagent, all right? So once you treat the ester with 2 moles of Grignard reagents, you work the reaction up, you end up getting a tertiary alcohol. 2 of the alkyl groups are coming from the Grignard reagent. That's the important part here, okay? So look at the left side over here, the whole butyl group, that is still there, okay? What is gone is what was attached to the oxygen over here, all right? And we'll see how that works in the mechanism, but this is what happens, all right? So the carbonyl carbon group, that stays, the oxygen group goes away. And 2 of the R groups, they actually come and attach on this carbon. So you end up getting a tertiary alcohol, right? And then the other alcohol is a side product, okay, which will come out when you do the workup. So how does this reaction work? So here's your Grignard reagent. Here's a random ester. It could be anything, all right? And remember, this oxygen over here, this oxygen group, the alkyl group here, this is going to go away. So you can literally have anything over here. The most important part is the left side of the carbonyl, because this is the group that is staying. This is leaving. So you can have methyl, ethyl, propyl, whatever you want, okay? Because that's going to leave. All right, so here's the Grignard reagent. Here is the ester. The ester here, okay, the starting point is the carbonyl, all right? So again, the alkyl group attacks the carbon, and then you end up getting this intermediate. Now, this is the part that is different from what we did with aldehydes and ketones, because now when the oxygen, when the Grignard reagent, okay, needs to go away, the electrons are given back to the carbonyl, and then the OR group, which is the oxygen group that we were talking about before, that is the one that goes away. Okay, and once that goes away, the OR goes away, then you end up getting a ketone, all right? And see why these brackets are written. Let's talk about that, okay? These brackets indicate that this is either an intermediate or a transition state, okay? And so this one over here is a transition state. This one here is an intermediate. Typically, when you're trying to do these reactions, you don't want to stop at the ketone. It's very unusual to stop at a ketone, okay, for this reaction, which is why this is written in a square bracket, which means that really you should plan on going all the way to the alcohol, okay? Once you get the ketone, the mechanism is exactly the same as we had for ketones, which means that now here comes the Grignard reagent, attacks the carbonyl, here's the intermediate. You work it up using a slightly acidic water, acidic hydrolysis, and you end up protonating the alcohol. So then the 2 R groups are coming from the 2 Grignard reagents. One over here, initially with the ester, and one here with the ketone. Okay, and again, don't stop in the middle with the ketone, no need to. Okay, there are other ways that you can actually make ketones. This is not a very good way of making ketone, okay, because it's very hard to control the reaction. But in any case, if you're using esters, the only thing you have to watch out for is that 2 of the alkyl groups are coming from the Grignard reagent, all right? Now for planning a synthesis. So far what we've done is we've gone forward, which means that you had the Grignard reagent, you had your substrate, and you did the reaction to figure out what your product will be. But what if you were given the product, okay, which means that what if you're asked to synthesize a particular alcohol and you were asked to figure out what kind of Grignard reagent and what kind of an aldehyde or a ketone or ester, okay, would you need to make that kind of an alcohol. So here's an example, okay, and remember these things are called retrosynthesis when you work your way backward, which means if you're given a product and you're supposed to figure out the starting materials, you're going to have to go backward, retrosynthesis. So here is the product, 3-phenyl 3-pentanol. Okay, and so this is an alcohol, obviously. And the starting material can be a ketone or an ester. Why? Here is your structure, okay, of the alcohol. So 1, 2, 3, 4, 5. 5 carbons. On the third one, you have a phenyl group, and on the third one, you also have the alcohol. So why is it can be a ketone or an ester? Well, look at this alcohol. It's a tertiary alcohol. So if you have a tertiary alcohol, then you have two choices. You can start from a ketone or you can start from an ester. If you had a secondary alcohol, you would start from an aldehyde in the Grignard reagent. If you had a primary, then you have no choice. The only thing you can use is formaldehyde. Okay, and so especially if you're trying to do a Grignard synthesis. So here is the structure. So now where do you break this? Where do you fragment? Because when you do a Grignard synthesis, you're actually forming a carbon-carbon bond. So when you're forming a carbon-carbon bond, it means that you actually need fragments. Okay, you need to combine 2 fragments together in order to form one compound. So we need to fragment our product to figure out what kind of fragments we need. All right, so we'll start with one fragment over here. And the fragment we want to take off here first is the phenyl group. Okay, so if we take off the phenyl group, that means that it is by itself. We are leaving the alcohol behind. If you leave the alcohol behind, then this group over here is the one that's going to be the carbonyl group, which is the ketone, because we need a ketone because this is a tertiary alcohol. And then the phenyl group will then become the Grignard reagent. Okay, and then now you can write the forward synthesis, which is that you need phenyl, magnesium, bromide, C6H5MgBr, and then you need the ketone, okay, which is 3-pentanone. Don't worry about the nomenclature yet. And then you need the ether, and then again, remember this is 1 and then 2, which is the acidic hydrolysis, and you end up getting your product from here. And remember, this arrow is the retrosynthesis arrow, and that is why these are your starting materials. This is your product. So now the starting materials are on the left side here because this is a normal reaction, forward moving reaction. Here's what you would do if you were to start with an ester. Okay, and so now because these 2 fragments here are the same, which is the ethyl group here and an ethyl group here, this is the only reason why you can use an ester. If all the 3 fragments were different around the alcohol group, then you could not have used an ester, because to use an ester you would need 2 moles of the Grignard reagent, and the 2 moles of the Grignard reagents have to be the same. You can't have 2 different ones. Okay, and so the only reason we are doing this with an ester is because of these 2 groups over here, or the symmetry in the molecule. Okay, you have 2 same groups. All right, so now what we'll have to do is we will have to fragment it right here at the CH2 and at the CH2. All right, so once we fragment those 2 out, we know that those 2 are going to become our Grignard reagent. Why? Because they don't have any oxygen on them. Okay, the fragment with the oxygen is going to be the one that is going to be the carbonyl. All right, and in this case the carbonyl is not just a carbonyl, it is an ester group. Okay, previously we had a ketone, now we have an ester. What I choose over here is kind of irrelevant. Okay, as I said, this is a leaving group, so you can use OCH3, you can use OC2H5, whatever ester you want, methyl, ethyl, propyl, whatever it is. Okay, it doesn't matter because this is going to go away. The important thing is I have an ester. So here's the forward reaction, my 2 moles of Grignard reagent, my ester, and then of course here's the product. Okay, so there are 2 ways of making this compound. There is another way that you can make this compound, and you should choose your own. Okay, so or try to do the third one yourself. Typically if you have a tertiary alcohol with 3 different groups on it, okay, then you have 3 different ways of making it. All right, and in this case you have at least 2 different ways, and then 1 more using another ketone. Okay, try that on your own. So this is how you would plan a Grignard synthesis. Now for using lithium and alkynide reagents. Lithium reagents are very similar to Grignard reagents. They're not that different. Alkynide reagents are slightly different in the sense that they have an alkyne group on there. Okay, so first of all, let's talk about lithium reagents. The organolithium reagents work exactly like the Grignard reagents. The only thing about the lithium reagents are that they're a little bit more water sensitive, and they're also reacting much faster than Grignard reagents, which means you have a lot more control over your reaction when you use Grignards. So lithium reagents will work just fine if you know exactly what you're doing and you have good technique, all right? So again, here is your organolithium reagent, just like Grignard reagents. It will attack the carbonyl and you get the products, okay? So again, you can use formaldehyde, an aldehyde, or a ketone, or an ester for that matter, in order to get the alcohol. But again, if you had to choose between organolithium and Grignard, I would choose Grignard, okay, all the time to make an alcohol. The alkynide ion is slightly different because the alkynide ion is coming from the alkyne, all right? And so here's an alkyne, and we know that this proton here attached to the carbon triple bond is the acidic proton. So when you treat it with a strong base, then you end up getting this alkynide ion, C minus, and this is also in a way an organometallic reagent because you have an ionic bond, okay, right here with sodium. So it can react just like a Grignard reagent because here is your very strong nucleophile. This is not a very strong acid, okay? It's fairly okay, but not really a strong acid, which means strong acid gives you a strong, a weak acid gives you a strong conjugate base. So this is a fairly good conjugate base, all right? And so the reaction is very similar to what you would do for organolithium or Grignard reagent, which means here's your negative ion, the carbon anion, except it's alkynide because it's on the triple bond, will attack the carbon, and this is how you get the product. Same mechanism, everything is the same. The only advantage that you have here is that you now have two functional groups. So you have an alkyne and you have an alcohol. So if you wanted to do other reactions on alkyne, like addition reactions, then you can now do that. Okay, so which means that you've just made your product a little bit more versatile. Okay, if you just wanted to add 3 carbons alkyl group, then you would just use a Grignard. But this just gives you a little bit more functionality to your product. All right, so depending on what you're trying to synthesize, you choose the right kind of reagent, organometallic reagent. So let's look at a few more examples over here for synthesizing alcohols. So here are your 3 alcohols. The first one is tertiary alcohol, the second one is tertiary, and so is the third one. Okay, and so they're all tertiary alcohols. Read the question carefully as to what it's asking you. Okay, so for example, here it says synthesize the following alcohols using the appropriate alkyl halide, and of course the other component has to be the carbonyl. Okay, so in some cases you have a choice, in some cases you don't have a choice. And when it says appropriate alkyl halide, it means that you have to take the Grignard reagent and show the alkyl halide that you're using to make that Grignard reagent. Okay, so let's look at the first one here. All right, so here we have a tertiary alcohol. If you have a tertiary alcohol, then you know that you need a ketone. Okay, so you can fragment this molecule. The best way to fragment is actually over here. I don't think you can fragment it any other way because sometimes there's more than one way to fragment it. But this one seems to be the best right now. Okay, that you fragment it right here at the ethyl group. Okay, and so then you get this ketone, and then here is your Grignard reagent. Okay, which then you will make from ethyl bromide. Okay, so the way you would make this is that you will take the ethyl bromide, treat that with magnesium, get the Grignard reagent, and once you treat that with the ketone, you should get your product. Okay, so that's how the synthesis will work. So the important thing for all of these alcohol synthesis is actually the fragmentation. Okay, how do you break your molecule apart? Here is another one. So now in this case, you can see already that it's a tertiary alcohol. And in this case, you have CH3 over here and you have 2 phenyl groups. So already, hopefully your mind is thinking, oh, I can use an ester or I could use a ketone. Okay, and so this synthesis here is given by using an ester. When you use an ester, then you can't use the C6H5 as your base molecule, okay, or as a substrate or as the carbonyl, because these 2 groups then will be coming from the Grignard reagent. Okay, so the way you make the Grignard reagent is by treating phenyl bromide with magnesium. Okay, so that is how you would make this. And here is the forward synthesis where you have the phenyl bromide, C6H5Br, treating that with magnesium, getting the magnesium bromide, and then of course with the ester, you end up getting these two groups here, okay? The mole ratio is not shown here, but this should be 2 moles, okay, of the Grignard reagent. And then here is the one with the alkyne. So as we just did this in the previous slide, it's kind of straightforward. The only place where you can break this apart is, of course, at the alkyne. All right, so you have a ketone, you have the alkynide ion. The alkynide ion is coming from the alkyne. And so you take the alkyne, treat that with a base, and you end up getting this alkynide ion, which when treated with ketone will give you your product. Okay, so go over these syntheses again in order to kind of see how the fragmentation is done. So finally, what I would like you to know from this chapter is, of course, the synthesis of alcohols from alkenes, and that would be just simple alcohols and then diols and then reduction of the carbonyls using the variety of different reagents, okay, of strengths like lithium aluminum hydride, sodium borohydride, and of course the last part that we covered with the organometallic reagents, the Grignards and all. There are some mechanisms that are really important, so please go through those, and of course remember about the Markovnikov, anti-Markovnikov, and syn and anti-additions and all those kind of things.